Hello everyone, welcome to the third lecture of the series on deep learning for control. In this lecture, we will be discussing feedforward neural network and its applications in control. Here is the overview of this lecture. We will be starting with a brief description of feedforward neural network or FNN. Then we consider a particular application in control which are based on soft sensors. Then we will briefly discuss different variants of FNN that are in the literature. Feedforward neural network or FNN is a network of neurons arranged in layers, and these layers are connected sequentially. And the sequential or feed-forward connection of layers is the main feature of FNN. Examples of such networks we have seen already in the last two lectures. And it is also one of the most popular versions of neural networks. A feed-forward neural network can be mathematically represented as in equation 1, which is basically a composite function containing L layers, where this F1, F2 till FL are the layers of the neural network. And X is the input to the neural network, and Y hat is the predicted output. Each of these layers will containing a different number of neurons. This figure we have seen in the previous lectures. Here F1 is the first hidden layer, and FL-1 is the L-1 the hidden layer, and FL is the output layer, and F0 is the input layer. And this input layer is simply passing the data. And after that, each of these layers we can represent as a composite function as in equation 3, where sigma is the activation function, A is the weight matrix, and BA is the bias vector. In feed-forward neural network, the information passes from each layer to the next layer only. The information flows in only one direction. That's why it's called a feed-forward neural network. Now, the training input and output for the FNN can be represented as in equation 4, where this X will be containing the input samples, which are X1, X2 till XD, and the matrix Y contains the output samples, which are Y1, Y2 till YD. Then using FNN, we can compute the predicted output, where Y1 hat is FNN of X1, and Y2 hat is FNN of X2, and so on. We can define the parameter vector for FNN as in equation 6. Here this A1 is the weighting matrix for the first hidden layer, and this A1C is a column vector obtained by rearranging or reshaping the weight matrix as a column vector, and B1 is the first bias vector. We have ALC, which is the weight matrix for the Lth layer rearranged as a column vector, and BL is the bias vector. So this entire thing we can represent as a column vector, which is the parameter vector. Then the loss function for neural network can be defined as in equation 7, where we have summed the prediction error across all the samples. And this we can also represent as the Frobenius norm of the output matrix minus the predicted output matrix squared, which can be expanded like this. Now, the optimization problem for FNN is to find the optimal value of the parameter vector theta, which minimizes the loss function. This is a nonlinear programming problem for which we can obtain a solution by using various iterative methods, which starts with an initial solution theta 0 and the updated solution iteratively. We have theta k plus 1 will be theta k minus alpha times gradient of the loss function with respect to theta. Alpha is a learning rate. Gradients can be computed efficiently using backpropagation method, which is based on the chain rule of differentiation. Next, we consider a simple application of this neural network in control, and this is based on the soft sensors. Soft sensors are software-based tools which are commonly used in advanced process control or APC. And these soft sensors are used for estimating variables that are not directly measurable. Here we have considered n number of input variables, which are like physical variables that we can directly measure. And using this, we can estimate the variables which are difficult to measure directly. Normally in industries, people use linear regression model, which can be represented as in equation 10, where the predicted output is a linear combination of different input variables, and we can also add a bias term. This can be represented as beta 0 plus beta into x, where beta is a coefficient vector which contains all the coefficients of this equation, and x is like a column vector which contains all the input variables. In many of the cases, this relationship may not be able to approximate using a linear model. So in that case, we can go for neural network based soft sensors as well. where the predicted output is only a function of the input vector x, and theta will contain all the parameters in the neural network model. In practice, in industries, this relationship between variable to be predicted and this physical variables will be nonlinear, because there can be many nonlinearities present in the system, such as saturation, dead time, etc. And if the process operating points are changing over a wide range, and if we need to have the soft sensor to predict well during the wide operating range, we should go ahead with the nonlinear models such as neural networks. In petroleum industries, soft sensors are commonly used for estimating boiling points of crude oil and its various fractions. Also used for estimating the percentage of impurities in the crude oil, such as sulfur, nitrogen, etc. And also used for estimating quantities such as viscosity, density, etc. Here we can see different fractions in a crude oil, which are naphtha. LGO stands for light gas oil, HGO for heavy gas oil, and each of these component has different boiling points. Based on this, there are different parameters such as initial boiling point, which is the temperature at which the first drop of this particular fraction is formed. For example, if we want to know the initial boiling point of naphtha is this particular temperature. Similarly, there are many other factors such as 5% cut point, 95% cut point, etc. These are the temperature at which 5% of that particular fraction is formed, like that. And these boiling points are difficult to measure directly because these are a factor of the chemical composition. Like if the particular fraction containing many impurities such as sulfur, etc., then this boiling point can change. And if you want to measure it, we have to do some experiment. And in the industries, we normally do this experiment at a lab. So we collect samples of this fraction and estimate its boiling point in lab. That takes a lot of time. In the industries, it is normally done once in a day or like that. These quantities, we use it in control application where we need real-time estimate of these quantities. For that, we can use soft sensors where we will estimate the boiling points or like these parameters using the physical variables which are directly measured. This will give us a real-time estimate of these quantities, which we can use for defining various constraints in the control problems such as model predictive control. Here we discuss a numerical example to illustrate neural network based modeling. In this example, we consider a regression problem in which the output is a continuous variable and our objective is to train a neural network model which predict the output given the input variables. First, we can import all the libraries. Here we are importing NumPy, Matplotlib, and sklearn libraries. And this MLP regressor is a particular class in the sklearn library which contains functions for neural network modeling. Now, in this example, we consider two input variables which are denoted by xtr1 and xtr2. And here k denotes the sampling instance and k goes from 0 to 100. And xtr1 is defined as a function of k, where this RNG denotes random noise. And xtr2 is also defined as a function of k. Then this xtr, which is the training input, contains both the xtr1 and xtr2 as its variables. The training output or YTR is defined as a nonlinear function of xtr1 and xtr2, where it is defined as 0.5 times xtr1 square minus 0.2 times sine of 0.1 xtr2. Then using this data, we can train a neural network model. And here we define the model using the MLP regressor function, where we consider 3 hidden layers. And for each hidden layer, the number of neurons is chosen as 10, which we can adjust later on. And the activation functions are chosen as ReLU. And the solver for the training problem is chosen as LBFGS. Now, using the training input and output, we can fit a neural network model to this data. And after that, using the trained model, we can predict the output. And the predicted output is denoted by y hat. Then we can plot both the actual output and the predicted output, where the actual output is plotted in red color and the predicted output is plotted in black color. Now, if we run this code, we can obtain the output as shown in this figure, where we can see the actual output in red color and the predicted output in black color. From this plot, we can see that the predicted output sufficiently approximates the trend in the actual output data. We can also try with different hidden layer sizes. Let's say if we consider the number of neurons in the hidden layer as 5, we can obtain the prediction as shown here, not as good as the previous one. If we add one more layer with 5 neurons and repeat the problem, then we can say the performance is improved. So here it is able to predict all these time instants. And we can also try with other activation function as well. Let's say instead of ReLU, we can replace it with the tan hyperbolic and rerun the problem. And for that case, we obtain output as shown in this figure. Here also, it's like the prediction is sufficiently good. In general, the prediction accuracy depends on the number of layers and the number of neurons per layer. So these parameters we can select by trial and error. We can use a portion of the data as testing or validation data set. And we can evaluate the training and validation performance to decide the number of hidden layers and number of neurons per layer. This example can also be considered as a soft sensor problem, where we have the actual output, which can be considered as some boiling point, as we discussed earlier in this lecture. And let's say this boiling point is like difficult to estimate in real time. And we have this boiling point estimate, like lab samples are available once in a day. We have this data is available for 100 days, which means like we have 100 samples of this boiling point estimates are available. Now we have the 2 input variable, or we can have more than 2 as well. Let's say the input variables are like some temperature and pressure in the reactor. For these variables, we have sensors are available and we can measure them in real time, let's say in every second or like once in a minute. But for the boiling point estimate, we have to do some lab experiment to estimate this value, which is performed only once in a day. Now, using the available data, like we have 100 samples of lab data is available, and we can take the input values for that particular time instant and train a neural network model as shown here. Now, once the model is trained, we can use that model for predicting these boiling points in real time. So it will predict this boiling point for each second, given the input data at that particular time instance. This is one way of using neural network models for soft sensors. Sometimes it can also occur we have a sensor is available and that particular sensor is not working. Now, instead of buying a new sensor, we can try a neural network model where we can use the past data when the sensor was working to train a neural network model. And using that model, we can able to predict it for the future. We can also use a feedforward neural network for dynamic modeling. In that case, we will be considering input and output data as in equation 20, where this input data is the control input at different time instance, which is denoted by u0 till ud minus 1. We have capital D samples of the input vectors and output data containing the sensor output, which is y0 till yd minus 1. Then feedforward neural network can be trained as a nonlinear dynamic model, which is in the form of nonlinear autoregressive model with exogenous input, or which is also called as NARCS model. This model can be represented as in equation 13. Here the neural network predicts the next value of the output, where it takes the current value and also the past ny values of the output, where ny is the number of past values which are considered, and also it takes the current and past values of the input. Here it's a dynamic model because we predict the next output using the current and past information. Different variants of feedforward neural networks are introduced in the literature. These are RBFNN, which you will be using radial basis functions such as Gaussian or polynomial spline, etc., as the activation functions. And the other variants are convolution NN or CNN, which is a regularized feedforward neural network, commonly used for image processing applications. Variants such as graph neural network, which is designed for processing data that can be represented as graphs. And there is physics informed neural network, which uses physics based information as a regularization term to improve the prediction capabilities of the neural network model. And the other variants are deep operator network or deep ONet and KN, etc. That leads to the end of this lecture. Thanks for watching.